Alright, so welcome back to the final module of the second week on branching algorithms. So this time we will be looking at some applications of the algorithm that we developed in the previous lecture, where we were focused on a new above guarantee parameterization for vertex cover. And back then we promised that we will show you why this algorithm can also be used to solve some other problems that don't really look like vertex cover at all. So those are the problems that we will be meeting in this lecture. They will be two brand new problems that you haven't seen so far, and this is going to be very exciting. In case you haven't seen the previous video, please do watch that one before coming here, at least to the point where you're comfortable with what we did show there, because we're going to just assume that as a black box for this video. And before we get started, I want to introduce you to a slightly different above guarantee parameterization for vertex cover, and this is the problem of vertex cover above matching. So here the parameter we want to look at is k minus mu of g, where mu of g is the size of a maximum matching. If you remember, we mentioned this parameterization in passing in the previous video, and I said that if you parameterize above LP opt, that would be in some sense a stronger parameter in quotes. Let's explore what that means, right? So suppose you have two parameters p and q, and let's say you know that one of these parameters is always smaller than the other one or is bounded by the other one, right? So let's consider these two possibilities here. I want to claim that one of these statements is true. So if a problem is FPT with respect to one of these parameters, then it implies that the problem is FPT with respect to the other parameter as well. But which one implies which? So take a moment here, pause, and make sure that you have come to a conclusion about which option you want to bet on. Alright, so the correct answer is that if a problem is FPT with respect to P, then it's FPT with respect to Q. And the reason for this is just consider the running time of your FPT algorithm, right? It's some f of P poly n, and that's just automatically at most f of Q poly n because of what we are given here. Intuitively also, it's as if somebody has given you just more wiggle room, somebody has given you a more generous parameter to work with. So if you were able to come up with an algorithm when you were constrained and in tighter circumstances, then of course you're going to do well when you have even more resources at your disposal. On the other hand, if you had a FPT algorithm in Q to begin with, and then somebody asked you for a FPT algorithm in P instead, then it's not clear that you can automatically just rely on the known FPT algorithm in the larger parameter. It really may not have any implications for the smaller parameter P. In fact, the whole complexity status of the problem may even change as you go from Q to P. So in general, going from Q to P is sort of a more challenging uphill task and certainly not automatic. But if you're doing well with respect to P, then you're automatically doing well with respect to Q. Now, if you think about the two parameters that I'm proposing here, so on the one hand, we have k minus mu of g, and on the other hand, we have k minus LP opt from last time. You can work out that k minus mu of g is actually the larger of the two parameters. And the reason for that is mu of g is at most LP opt. LP opt is in general at least the size of any maximum matching. So in some sense, you're taking away less from k when you take away the size of a maximum matching compared to when you take away the LP opt. So this just happens to be the larger of the two parameters. So we already know that vertex cover parameterized by k minus mu of g is FPT with the same running time, so 4 to the k minus mu of g. And why am I telling you all this? Why are we starting off by weakening a stronger result? Well, it just turns out that this formulation of the problem is more useful or more convenient to work with when we get to the reductions that we want to do. So this is the problem that I want to keep at the back of our minds as we go through this lecture. So I hope that's clear. And now we can transition to the first problem that we want to talk about, which happens to be the problem of finding an odd cycle transversal. So what is an odd cycle transversal, or a OCT for short, in a graph G? As always, we will be working with simple and undirected graphs for this discussion, and an OCT for such a graph is simply a subset of vertices whose removal makes the graph bipartite. Equivalently, you can think of OCT as a subset of vertices that's interested in killing cycles, much like FVS, a problem that we met recently. But unlike FVS, an OCT does not want to kill all cycles. It's only interested in targeting the cycles that have an odd number of vertices in them, and hence the name odd cycle transversal. Notice that these two definitions that I've mentioned, deleting to get a bipartite graph and deleting so that you intercept all cycles of odd length, are in fact equivalent, because you might remember that a graph is bipartite if and only if it does not have any cycles of odd length. As usual, let's just establish some familiarity with the problem simply by going through a small example. So I'm going to show you a graph and I'm going to ask you to figure out what's the smallest OCT for this graph. So take a moment here, pause the video if you need to, and try to figure out what would be a small OCT for this graph. Of course, small is relative, just come up with the smallest that you can find. Yeah. All right, so hopefully you had a chance to think about that. And a first observation that you might make is the following. If you decide not to remove the vertex W, which seems to be at the center of this spider web thingy here, if you decide to not remove it, if you decide to not include it in your OCT, then you're essentially left with these four triangles to worry about, which are disjoint except for the vertex W. And since you have, let's say you've committed to not picking W, each of these triangles is going to demand a special place of its own in the OCT. So any OCT that chooses to ignore W must already pick at least 4 vertices. Now that sounds kind of expensive, so maybe it's a good idea to start by picking the vertex W. Now once you've picked the vertex W, notice that this is the graph that you're left with. Maybe I should show you the graph that we started with as well. So W is gone and you're left with these sort of 4 matching edges, and then you're left with the vertex Z, which sort of connects to them in this particular way. So notice that you're still left with 1 cycle of odd length. So one way of getting rid of that cycle is to, for example, get rid of the vertex Z, although you could pick any one of the other vertices on the cycle as well. And I believe that should work, although to be honest, I haven't checked. But in any case, W, Z is a valid OCT for this graph of size 2, and notice that you can also convince yourself that you do need at least 2 vertices. So in that sense, this is optimal. It's not very hard to see that you have, for example, this odd cycle, and you could pick one of WAB or WXY as another odd cycle which is disjoint from this one. So just like we've been saying for problems like vertex cover and FVS, if you have multiple disjoint obstructions, then that's a lower bound for how many vertices you need in your solution. So we have 2 disjoint cycles of odd length, so any OCT here would have to have size at least 2, and so we were fortunate that we found one that has size exactly 2, and therefore that's going to be optimal. As always, the computational question associated with this definition is the question of finding an OCT that has the smallest possible size. And we will, of course, be working with the decision version of the problem where we are looking for an OCT of size at most k for a given budget k. So that's the problem that we will be working with. So if you like, spend some time thinking about, your own approaches to coming up with an FPT algorithm for this problem. For instance, you might think about just generalizing the algorithm that you learned for FVS, or just trying to branch on short cycles of odd length. All of these are good places to start, and if you'd like to take some time now just to think about the problem, then please feel free to do that. As I promised earlier, in this particular lecture, we are not going to be coming up with algorithms from scratch, but we will be trying to leverage the algorithms that we have already developed in the previous lecture. So once you're ready and once you come back, what we are going to be doing is we will be transforming instances of odd cycle transversal into instances of LP above matching. So that's going to be an interesting experience. So let's get started if you're ready. So here is what we are going to do. Let's say we are working with an instance of OCT, and this is just one concrete example to make it easier to see what's going to happen. So suppose this is the instance of OCT that you're working with. We're going to convert this to an instance of vertex cover as follows. So we're going to make two copies of the graphs. So you can see the two copies drawn out in black here. And on top of that, we are going to add a matching. And the way the matching is designed is that it's going to add an edge between two copies of any original vertex. So for instance, if you focus on the vertex A here, it's manifested twice, and we label them A1 and A2 just to keep track of where it came from. And now you have an edge that connects A1 to A2. And similarly for B and C and so on, all the remaining vertices. So in general, if you started with a graph on n vertices, you're going to obtain a graph on 2n vertices and 2m plus n edges. So all the original edges are going to be duplicated. So you have two copies of them. So that's the first 2m edges. But on top of those original edges, you're also going to add this matching. So that's going to be an additional n edges. Okay. All right, why is this construction interesting? What are we going to get out of this? Well, it turns out, and this is where all the magic happens, it turns out that if G is a graph on n vertices, and if this graph that we just built out, you call it G tilde as we have done here, then the following is true. G has an OCT of size at most k if and only if G tilde has a vertex cover of size n plus k. This is really cool, I must say. If we can show this, then notice that we already have a 4 to the k algorithm for OCT. And how is that? Well, notice that n is the size of a maximum matching in this graph. So if you were to parameterize this vertex cover instance by the above guarantee parameterization that we started with, which is k minus the size of a maximum matching, then notice that k minus the size of a maximum matching really amounts to the k that we have here for OCT, right? So you have an algorithm whose running time is 4 to the k minus the size of a maximum matching, where k is the size of the vertex cover that you're looking for, and the size of a maximum matching is n. So that's going to be n plus k minus n, which is k. So the running time of your vertex cover algorithm, the algorithm that we described in the previous lecture, is going to be 4 to the k, where this k is now the k from the OCT instance. So hopefully you can see that once you show this equivalence, you have your OCT algorithm, and that's why we should be all motivated at this point to actually establish this equivalence. Once we do that, we are in fact done. Okay, so let's try to show this, right? So this is what we want to show. G has an OCT of size at most k if and only if G tilde has a vertex cover of size at most k. By the way, you might just want to make a quick note of how the reduction works, or just commit it a little bit to memory, because this is something that we will be working with. You have G, you have G tilde. G tilde is two copies of G and a matching between the duplicate vertices, a matching that matches every vertex to its copy in G tilde. So with that out of the way, let's get started with proving the first of these two statements, which is to say that if G has an OCT of size at most k, let's show that G tilde has a vertex cover of size n plus k. So let's start with G. Here is G, and let's say this is some OCT of size at most k. This is a very abstract version of G. I'm no longer working with the specific graph that we started with. So at this point, the discussion is just going to be about some generic graph G, some generic instance of OCT. So the assumption, remember, was suppose G has a OCT of size at most k. So let's set the OCT aside. Let's keep it on top. Let's call it x. So this is the OCT of size at most k. And let's say it leaves behind a bipartite graph when it's deleted. So this is G minus x. And let's say G minus x is bipartite with bipartitions A and B. Okay. Let's try and see what this picture looks like in G tilde. Okay, so how do these subsets manifest in G tilde? Remember, we have two copies of everything, so that's what this is going to look like. So in G tilde, let's say these are the two copies of X, and we also have two copies of A and two copies of B. And remember that AB induce bipartite graphs, so even in these copies, you're going to have a bipartite graph here and a bipartite graph here, which is to say there are no edges inside A1, B1, A2, or B2. So by the way, I'm using capital A1 to denote the subset of vertices, which constitute the first copies of the vertices in A, A2 to denote the second copies, and so on and so forth. X1, X2, B1, and B2, that's the notation, and hopefully that's clear. Now, what do we want to show here? What we want to show here is that, okay, we had an OCT of size at most k here, so we want to say that there's a vertex cover of size at most n plus k here. By just staring at this picture, can you spot this vertex cover of size n minus k? It's a combination of some of these boxes, and there are only so many boxes, so I suppose there are 6 boxes, so you have 64 options, but not really. I mean, at least you don't have to hopefully consider all of them. I think it's reasonably intuitive as to how you might want to construct the vertex cover by just observing where all the edges are and realizing that those are the edges that you have to make sure to hit. So just think about that for a minute. If you need to pause the video here, please do, and come back when you're ready. All right, so notice that this is a subset of size 2k, the two copies of X. That seems like a small price to pay, so let's just set those aside. Now here we have these edges going across. So notice that if we picked either A1 union B2 or A2 union B1, then we would cover everything. It wouldn't work to pick A1 union B1, for instance, because then these edges would be uncovered. It also wouldn't work to pick A2 union B2 because those edges would be uncovered. Similarly, it will not work to pick A1 union A2 because these matching edges would be left behind, and it wouldn't work to pick B1 union B2 for the same reason. Now, of course, you could pick any superset of the set that I described, but it turns out that because the set that I described is enough, that's what we'll stick to doing. So, for example, here I have the vertices from the two copies of X and A2 union B1. Now, what's the size of the subset that we have picked? So as we have already said, the two copies of X will cost us k plus k, that's 2k. And we are picking one copy of A from here and one copy of B from here. So notice that that's just essentially the same number of vertices as we have in A union B, but A union B is essentially n minus k vertices. So the total number of vertices here is k plus n minus k, which is essentially one of those k's cancel. So the total size of this highlighted subset, which is a vertex cover, is in fact n plus k. But remember, that's exactly what we were looking for. We wanted to prove that G tilde has a vertex cover of size n plus k. So we are done as far as the forward implication is concerned. So that's essentially half the battle. Let's now turn our attention to the reverse direction. So far we've built a vertex cover based on an OCT, and now we want to somehow go the other way. Now, just to remind you, G tilde is this graph here. And we want to say that if this guy has a vertex cover of size n plus k, then the original graph, G, that we were coming from, should have a OCT of size at most k. So let's try and show that now. Alright, so as before, let's start with a picture of G tilde with the promised solution made explicit. So remember where we are coming from. We know that G tilde has a vertex cover of size n plus k. So let's make that vertex cover explicit here, give it a name, let's call it y. And what we know is that G tilde minus y is an independent set. Now let me also bifurcate this independent set into two parts, and we'll see why we are doing this, but it's quite natural for me to segregate the vertices that essentially are the first copies of the corresponding vertices in G versus those vertices which are the second copies of the corresponding vertices in G. So for instance, if somebody gave you the independent set C1A2 in G tilde, then C1 would go to A tilde and A2 would come to B tilde, right? And notice that you will never have two copies of the same vertex sitting in G tilde minus y, because every time we had two copies of the same vertex, we explicitly drew an edge joining them, and this being an independent set, it's not going to bring in two copies of the same vertex. So for every vertex in G, we see at most one of its copies in G tilde minus y. That's a useful thing to keep in mind. Now from here, we want to somehow pull back an OCT of size at most k, and it might be more useful to think about it in terms of wanting a large bipartite graph based on a large independent set rather than a small OCT based on a small vertex cover. Of course, these are both exactly equivalent, but it's just more convenient for me to think about it the other way. So back in G, let's just bring up the vertices on which A tilde and B tilde are based, right? So let's just drop the subscripts and go back to the original vertices corresponding to these subsets here. And this is going to tell us something about why we are almost done. So let's ask ourselves these three questions. What can we say about the size of G tilde minus y? What can we say about the size of A union B? And what can we say about the graph induced on A union B? This is the original graph G. So what does A union B look like in G? Let's try to answer these three questions, and you will see that we have essentially proved the reverse direction. If you want to do this yourself, this is a perfect time to pause the video. Alright, so what is the size of G tilde minus y? We know that G tilde altogether has 2n vertices, and the size of y is at most n minus k. So when we subtract n minus k vertices from 2n, we are left with n minus k vertices. Did I just say we subtract n minus k vertices? That's not quite right. We subtract n plus k vertices, at most n plus k vertices from 2n, and we are left therefore with n minus k. So the size of G tilde minus y is at least n minus k. Also notice that A union B, which is essentially the size of A tilde union B tilde, is also at least n minus k, because we didn't have two copies of the same vertex. As we noted earlier, the intersection of A and B is empty, so the size of A union B is essentially the size of A tilde union B tilde. So we have n minus k vertices here. So hopefully that's all right so far. And now, what can you say about G induced on A union B? It should be clear that that's going to be bipartite. So notice that A and B are independent sets, because if there was an edge between two vertices of A, then that edge would have manifested in G tilde minus y as well, but we have promised that that's an independent set, so that cannot happen. So A is an independent set in G and B is an independent set in G, and A union B is a set of size at least n minus k. Therefore, anything that's not in A union B, if you just look at that subset, so the vertex set of G minus A union B, by definition, that's going to be a OCT, and by this calculation, that's going to be an OCT of size at most k. Therefore, we are also done with the reverse direction, and at this point, we have completed the argument for essentially why OCT admits an algorithm whose running time is 4 to the k. And we did this just by transforming an instance of OCT to an instance of vertex cover parameterized above the size of a maximum matching. So hopefully you've gotten the feel of the strategy that we are employing here. We are not coming up with a direct algorithm for the problem, but we are instead leveraging the algorithm that we already have for vertex cover parameterized by k minus mu. At this point, we're going to switch gears and talk about a different problem that we will solve using a very similar strategy, in that we will reduce it to an instance of vertex cover above matching. So if you want to take a break or just go back and make sure that whatever we have discussed about OCT is clear, this is a good intermission point. You can come back when you're ready. Okay, so the second problem I want to talk about is almost 2SAT. But before we can talk about almost 2SAT, we need to talk about 2SAT first. So hopefully you are already familiar with the problem of SAT. It's perhaps the first NP complete problem that you encountered. And 2SAT is a very, very special case of SAT, which actually happens to be polynomial time solvable. So let's recall what a 2SAT formula is in CNF form. So it's a Boolean formula which has the following format. It's essentially the AND of M clauses, where every clause is the OR of at most two literals. And a literal is simply a Boolean variable or its negation. So that's a 2SAT formula. And so in particular, if you gave me a truth assignment, truth values assigned to each Boolean variable that was involved in this formula, then we would say that the formula is satisfied by this truth assignment if and only if in every clause there is at least one literal that evaluates to true. So either a true literal that was set to 1 or a false literal that was set to 0. Any one of these combinations would work, but every clause has to have at least one such literal. That's true of any CNF SAT formula. The special thing about 2SAT is that every clause only has two literals in it, and it turns out that you can figure out if such a formula admits a truth assignment or not, which satisfies it in polynomial time. So that's great. It's always nice to have a SAT variant that you can actually tackle in polynomial time. But now suppose you were working with an actual instance of 2SAT, and let's say you run your algorithm, and let's further assume that your algorithm comes back to tell you that this formula was not satisfiable. So of course this is an objective truth. There's nothing you can do about it, and you could argue that there's no need to get emotional about this. You don't have to be happy or sad just because your formula was satisfiable or not. And that's true if you were doing this SAT business for homework. But in the real world, typically the reason people are solving instances of SAT in the first place is because it models some real world problem, and the solutions correspond to actual solutions. So if things don't work out, you would typically be disappointed. Now the question is, what's the next best thing you can do? That's always the question, right? So you couldn't satisfy the whole formula, but maybe could you come close to satisfying, let's say, most constraints? If so, then maybe that's a good situation to be in once again, and that motivates the definition of the almost 2SAT problem. Now there are two natural ways in which you can talk about almost satisfying a 2SAT formula. You could say, let's try and satisfy say 90% of the constraints, or you could also say that suppose I just eliminate a small number of variables from the picture, then can you satisfy the rest of the formula? So both of these are valid ways of trying to talk about being close to being satisfiable. So we're going to look at the variable version in this lecture. So the question is, given a 2SAT formula and a hopefully small budget k, can you remove at most k variables from the formula so that the rest of it is satisfiable? And what does it mean to delete at most k variables? Just means that you get the clauses that involve these variables for free. So you just eliminate all clauses that involve these variables in either positive or negative form. So just to get some practice with the definition of almost 2SAT, let's just think about a specific example. So here is a 2-sat formula, and I'd like you to take a pause here to think about whether the formula is satisfiable or not. And just in case it turns out to be not satisfiable, think about whether it's almost satisfiable with a budget of 1. So feel free to take a pause here and come back once you've had a chance to think about this. Alright, so the answer to the first question, as you might have guessed, is no, because we probably do want the second question to be a legitimate one. But you can actually argue that this formula is not satisfiable. One way to do it is, of course, to try all possible assignments to all the variables, but there's actually an easier way to do this, and that's by observing what happens if you try setting x to true and what happens if you try setting x to false. In both cases, you get essentially implication chains which lead to contradictions. Therefore, there is no satisfying assignment for the formula to begin with, because any such assignment would have to set x one way or the other, but no matter what it did, it would end up in a fix, and it's not going to be workable. On the other hand, if you remove this offending variable x from the picture, then a bunch of clauses go away and you're just left with these 3 right here in the middle. And it turns out that those are satisfiable, in fact, I think in more ways than one, but it's certainly going to be a satisfiable formula. So hopefully the notion of an almost 2-sat instance is clear by now, and we're going to solve this pretty much the same way that we solved OCT. We are going to build a graph based on this formula, and we are going to argue that this graph is a yes instance of vertex cover above matching if and only if the formula that we started with had a solution of size at most k. So I'm going to describe the construction first in abstract terms. I would encourage you to actually try and work through the construction for a specific example, but then I'll also work out a specific example with you, and then we will argue the equivalence. So let's start with the actual construction. Recall that what we are working with is a 2-sat formula phi, and that's what we need to convert into some sort of a graph so that the almost 2-satness of phi can be reflected in the size of the vertex cover of this graph that we construct. So here is how we are going to build the graph. For every variable in the formula phi, we are going to introduce 2 vertices, one representing the positive literal and one representing the negative literal. So just like we added a matching between the 2 copies that we created in the OCT construction, we are also going to add edges here between the x and x bar vertices that represent a single variable x. So at this point, your graph is just a matching. We haven't added anything else just yet. So this graph is capturing information about the variables, and we need to now also encode in this graph information about the clauses of the formula phi. So remember that phi was a 2-sat formula, and in a 2-sat formula, every clause has at most 2 literals. So we have clauses that have 1 literal and we have clauses that have 2 literals. So let's make a distinction between them. So if you have a clause that has just 1 literal in it, we are going to call these unary clauses. Then if you have a clause with the literal x, then what we are going to do is add a degree 1 neighbor to the vertex that's representing the literal x, and we have a unary clause with the literal x bar, then we'll add a degree 1 neighbor to the vertex that's representing the literal x bar. Now, if you're thinking ahead a little bit already and you're wondering why we are doing this, then in some sense, the very high level intuition is that we somehow want to say that if you have a clause which is just 1 literal, then that literal has to be set in the way that is dictated by that clause in any satisfying assignment. And our vertex cover is somehow going to correspond to a satisfying assignment. And so we are just whispering to the vertex cover that we are anticipating that, look, just go ahead and pick this vertex x or pick this vertex x bar. So these are going to be degree 1 vertices, which essentially force the choice of the neighbor. Remember that we have talked about degree 1 reduction rules before, and we know that there's always going to be an optimal vertex cover that picks the neighbor of a degree 1 vertex. So that's kind of what we are trying to do here. I think this will become more explicit as we go along. So if what I just said did not make sense, then feel free to just ignore it. It's nothing to worry about. Now, for the clauses that have two literals, we are going to go ahead and add edges between the vertices that represent those literals. And this is again trying to just tell the vertex cover something, right? We're trying to say, look, please go ahead and pick at least one of these vertices to ensure that this clause is satisfied. So that's the entire construction. This is the graph that we want to build. And again, let me just bring back the example of the 2SAT formula that we had a few moments ago. And what I would encourage you to do is to pause the video here and actually construct this graph for this small formula here, just to get a feel for what's going on. And you might even want to start thinking about the main claim that we want to make here. So just like we had with OCT, what we want to show here is that if you have a valid solution for phi comma k, right? If you have a subset of at most k variables that which when set aside make the remaining formula satisfiable, then you also have a vertex cover of size n plus k in the graph that we just described. So that's what we want to show. And once again, once you show this, you are done. You have the equivalence. You can then run the algorithm that we had from last time on this graph that we have just constructed. And because there is a matching of size n, remember that's what we added in the very first step, our above guarantee parameterization will ensure that the corresponding FPT algorithm has a running time of 4 to the k, where k is the standard parameter for the almost 2SAT problem. So that's what we want to show. So you might want to take a moment here to actually start thinking even about how you would show this equivalence. So pause the video and once again come back once you're ready. All right, so hopefully you had a chance to absorb the construction, and hopefully you've developed your own intuition for what the construction is trying to achieve. As I promised, we will go through an example together. So here's a different example just for variety. And I think this is the same example that you will find also in the textbook. So in case you're following along, then just wanted to alert you to that. So here is the formula on 4 variables here. So we have added these 8 vertices with a matching. So the matching is in the background and it's in black. We have one unary clause, so that's this degree 1 neighbor for the corresponding literal, and the remaining edges in red correspond to the clauses that we have here. And if you like, you can take a moment here to verify that hopefully there are no mistakes in this picture. Okay, so once you've done that, let's, I think, try to actually get back to the equivalence that we wanted to show. So we wanted to say that if you have a 2SAT formula and you build this specific graph based on it, then almost 2SAT solution corresponds to a vertex cover of a certain size. So if you have a solution of size at most k, then this graph has a vertex cover of size at most n plus k. So as usual, let's start with a forward implication first. So let's begin by saying, suppose you do have a subset of variables whose removal makes the formula satisfiable, and suppose that the fact that this formula is satisfiable is witnessed by tau, that's the satisfying assignment for phi minus x, and of course we are removing at most k variables. That's a part of the deal, that's a part of the assumption that we have. Now what's the obligation? We want to show that g phi has a vertex cover of size n plus k, and again take a moment here to think about what this vertex cover should be. it's reasonably intuitive, just working backwards from the anticipated size and knowing that for every matching edge, we do have to pick at least one of the endpoints. So it seems pretty natural to say that, whenever we have a vertex corresponding to an undeleted variable, let's try to pick that endpoint that tau sets to 1, and for everything that's chosen by x, maybe we can just try to pick both of the endpoints. So that's the solution that we want to build. In fact, let's make that explicit here. So if you have a variable that's picked in the solution, then we will include both of the vertices that are based off of that variable. And for every variable that's not in the solution, we are going to pick the endpoint corresponding to the satisfying assignment tau. Now, it should be clear that this set has size at most n plus k. Essentially, from each matching edge, we are definitely picking one vertex, but there are k of these variables that were included in X, and for those we are picking both endpoints of the matching edges. So we are picking k extra vertices on top of n, and again, this is something that you should take a moment to verify if you're not completely convinced yet. And now you also want to think about, why does this form a valid vertex cover? And the reason for that is essentially going to be based on the fact that tau is a satisfying assignment for phi minus x. So in particular, if you have an edge that's left over after you delete this proposed subset here, notice that it cannot be a matching edge, and the reason for that is we definitely picked at least one endpoint from every matching edge. So it's going to be either one of these edges that come out of a degree 1 neighbor, or it's going to be one of the red edges. But you can see that if any one of these edges are left over, then there is a clause that was not satisfied in phi minus x. Right? So again, I'm going to leave this as an exercise, although this should be quite evident from the construction at this point. So hopefully you can see that we have a vertex cover of size n plus k if somebody gives us a subset of k variables whose deletion makes the formula satisfiable. Now let's talk about the reverse direction, which is that if you had a vertex cover of size n plus k, then from that vertex cover you can recover a subset of variables whose deletion makes phi satisfiable. And again here, you might have already developed the intuition that you need to prove this implication. The idea is to observe that any vertex cover of size n plus k is going to have the following format. It's of course going to be compelled to pick at least one vertex from every matching edge, but because of this budget being n plus k, there are probably going to be about k edges from the matching, in fact at most k edges from the matching, where you end up picking both of the endpoints. And you might suspect that those matching edges where you're picking both endpoints correspond somehow to variables that you should be including in your almost 2-sat solution. Now you might of course say, what about these degree 1 vertices that we added that don't correspond to any variable? But again, because of our discussion about the degree 1 reduction rule, we know that we can always assume that we are working with a vertex cover that doesn't involve any of the degree 1 vertices. So that's what I wanted to point out here. So your vertex cover is essentially involving only vertices that correspond to real literals, and that's because of the fact that you can always exchange a degree 1 vertex that's in your vertex cover with its neighbor, and you'll still be left with a valid vertex cover of the same size. So with that out of the way, let's describe the satisfying assignment based on the vertex cover that we have. So if both the literals belong to our vertex cover, then we include the corresponding variable in our solution, and otherwise we are going to set the variables based on how the vertex cover has chosen from the corresponding matching edge. So this, in fact, right here is a witness for why phi minus x admits a satisfying assignment. So the reason this is a satisfying assignment is that if it wasn't, and if there was a clause that was left over, then the leftover clause which did not get satisfied would correspond to an edge in this graph that was not covered by our vertex cover, and that would be a contradiction. So that's essentially the basis of the equivalence of these two instances. So we have this main lemma here, and essentially based on the algorithm that we already have seen, we get for free pretty much modulo this reduction 4 to the k algorithm for the almost 2-sat problem. So hopefully these arguments made sense. Do reach out and let us know if you have any questions. You could either post your questions in the comment section of this YouTube video, or you could reach out to us on the Google Groups mailing list that has been set up for this course if you are enrolled through SWAYAM. So thanks so much for watching, and we will see you back next week.